Hi, my name is Park Kelly, and this is my video going over Design Assignment 5 report. My group members were Hannah, Edward, Pedro, and Ashley. In this report, I mainly worked on the Flex and Maple, as mine were the final versions of both, as well as I helped out in the report. We'll be first looking at the problem definition. So, the problem this time was to design a quartz and titanium bridge resonator sensor for thin film deposition measurement to optimize its sensitivity. The constraints we had for this problem were the length, width, and thickness of the bridge structure, the thickness of each layer, the length of the deposition window, with the goal to maximize for the greatest range of mass that the system can be sensitive to. Most of these constraints related off of the length of the bridge, with things like the thickness of the bridge having to be within 5% to 20% of the length, as well as the window length being 5% to 40% of the bridge length. Additionally, we had to look at the longevity of our materials as well as the sensitivity for thickness plots. This here is a diagram of what our bridge should look like, with the window, quartz, and titanium metal present, with length in the Y, width in the Z, and thickness in the X. Looking at background theory, you can assume that our bridge is like a beam, and then we can look at it through the lens of Newton's laws to a small portion of a beam. You can see here our equations for shear stress, looking at different harmonic solutions using the differential volume displacements, and looking at angular frequency, which will be solved with module analysis. Here are some parts of our code that shows where we added variables and what we used. All of our code is based off of the example problem of 5.32 constraints and QOL improvements for beam resonance. Further down here, we can see the Maple code, which we used to get the real curvature of the bridge, in which we used Professor Minnick's code from March 28th. Taking this curvature real equation and solving for m, we get that the thickness ratio equals 1 over the square root of the stiffness ratio, which got us to our final answer of 1.29. In validating the model, we looked at different plots of frequency of different geometrics and compared it to ours, and they all looked very similar. We also looked at the R model without and with the window and saw that it does change the answer, so the window was doing its job. And further, we knew it was bound on both sides, so it should be validated in that regard as well. Looking at scripting, the first thing here is our code of what we took out of the Flex using the export files. The two things we used to optimize this time around were the grid search and the gradient ascent. So grid search was first, and it went through 3 ranges of height, width, and length, and compared those values to find a trend, which you can see through our first plot here. Secondly, we went through gradient ascent, which goes through values until a peak, and then goes back over that peak repeatedly in smaller and smaller intervals until we get our max peak. We do not have any pictures of the plot. However, we did come to our final answer, which was a 4.54 times 10 to the negative 4 meters for width, 4.73 times 10 to the negative 4 meters for height, 7.34 times 10 to the negative 3 meters for length, and that comes out to a sensitivity of 2.10 times 10 to the 12. For final conclusions, comments, and limitations, in the conclusion, we do look at the lifetime of all the other materials we're supposed to, and get their ratios by comparing the two at different frequencies using the same dimensions. Doing that, we find that gold has the highest ratio for longevity, so thus it will last the longest. The limitations we had were things like the simplified simulation, so our module analysis in the simulation is simplified. The simulation assumes linear behavior. When our bridge is brought into the real world, there will be different things like temperature, pressure, and humidity that could affect it, as well as the module analysis does not consider the electrical properties of the QCM, such as impedance, capacitance, and the resonant frequency, which could all affect the sensitivity of the device. Thank you.